This is a video of a type that I've wanted to do for some time, and it's one of the reasons why I started this channel. So I've been following a few of these flat earthers on YouTube for a few weeks. It's a little bit like watching a train wreck or a car wreck or maybe some freak show in an old-timey carnival. Anyway, one of the problems that these guys have, and they have a lot of problems, is that they never actually calculate anything. Instead, they take things like gravitational theory and mathematics, and they kind of run them through a meat grinder until all that remains is incoherent gibberish. And then they proceed to debunk that gibberish and they say, see, the earth is flat. One of the main arguments that I keep hearing in these flat earther videos is that the world can't possibly be spinning at 1,000 miles per hour, which is the tangential velocity corresponding to an orbital period of 24 hours for a globe with a radius of 4,000 miles, because we would feel it, they say. We would be flung off into space if the globe were spinning that fast. Or if we jumped up into the air, we would land hundreds of feet away. Or flights would take longer traveling east to west rather than west to east. These things sound silly to most people, but flat earthers believe this sort of thing. I'm sure the vast majority of these guys have at least a free demo version of Microsoft Excel on their hard drive somewhere. If they would root around their drives and find it, maybe they would find it useful. I'm using Google Sheets here. Google Sheets is also free, and it's pretty convenient to use because you don't have to download software. It's browser-based, so you can just go to Google and start using it right away. At least one guy who I think could benefit from a spreadsheet package such as this is a guy named the Morgill. The Morgill often repeats his belief that the opposing forces of gravitation and the centrifugal force must equal one another at the equator in order for people to be able to walk around on a rotating spherical planet. He further rationalizes that if a person on such a world were to walk toward the polar regions where the centrifugal force is less, that they would somehow be crushed by an overwhelming force of gravity that's no longer balanced by an opposing force. This is false on multiple levels. First of all, if gravity and the centrifugal force were in fact equal and opposite one another at the equator, a person at the equator wouldn't be walking at all. Such a person would be weightless. This is in fact the reason why astronauts aboard the International Space Station are weightless. They haven't escaped gravity where they're at. In fact, the force of gravity at their altitude of about 250 miles is only slightly less than what it would be at the Earth's surface. Gravity is inversely proportional to the square root of the radius, so just do the math. R1 is the radius at the ground, which is about 4,000 miles, the radius of the Earth. R2 is the radius at the International Space Station. That's at an altitude of 250 miles, so 250 plus 4,000 is 4,250 miles. Now when you plug these values into the equation, you find that the force of gravity at that altitude corresponds to about 0.89 Gs. In other words, your weight at the altitude of the ISS would be about 89% what it is at the ground. Now obviously the astronauts aboard the International Space Station are weightless, but the reason isn't because they've escaped gravity. The reason is because they're traveling at orbital velocity. In other words, they're traveling at such a velocity that the resulting centrifugal force is exactly equal to the opposite force of gravity. Therefore, the net force on their bodies is zero. The Morgill, I think, could figure this out if he wanted to. I don't think the guy is particularly dumb. Rather, I think he's chosen a dogma that he wishes to believe in, and he willfully butchers and ignores math and physics to conform to that worldview. The Morgill talks often in his videos of the analogous situation of the Gravitron, the amusement park ride. He suggests in at least one video that if you were to take such a ride and double the radius but reduce the rate of rotation by half, that the force would remain about the same. That's false, and you would see that if you would calculate it. He then goes on to suggest that if you had a very large gravitron with a radius of about 100 miles, but running at only a few RPM, the result would be a crushing force. His intent here seems to be to suggest that as you scale such things up, the rotation rate necessary to produce a significant force decreases. In other words, that the Earth's orbital period of about 24 hours, while it may seem slow, nevertheless produces a significant centrifugal force because the Earth's radius is so large. He is right, at least with regard to his example of a 100-mile radius gravitron rotating at 3 RPM. It would indeed produce a significant force. But he never calculates anything. He doesn't calculate anything for that. He doesn't calculate anything for the Earth. And that's his downfall. If he would just take the extra step of punching a few numbers into a calculator, he would see this. So what I've done with this spreadsheet is I've held a force constant at 1g. And I've calculated the velocity necessary to produce a 1g force, a centrifugal force of 1g at a given radius. And then I've graphed it, and what you see me doing here is just going back and adding some grid lines. And then I can maybe show you a couple of things with the result. Okay, looking at the blue line, you can see that with a radius of 4,000 miles, which would correspond to the radius of the Earth, on the vertical axis, that corresponds to about 18,000 miles per hour. So that would be the velocity necessary on the Earth's surface to produce a centrifugal force of about 1g. And then on the other extreme, if you follow the blue line way down to the close to zero, and you look at a velocity of 1,000 miles per hour, you can see that is the value that corresponded to a radius of about 13 miles. Okay, these values here that you're looking at, this is a separate spreadsheet. All I've done is I calculated the force for the Morgel's centrifuge, radius of about 5 meters. I don't know exactly if that's the radius, but looking at the pictures, I guesstimated the radius to be about 5 meters. And well, first of all, I compared that to the situation if you were to just double the radius but reduce the RPM by half. So initially we have a 5 meter radius centrifuge with 24 RPM speed, and that produces a g-force of 3.2, which is about right. The gravitrons produce about 3 g's force, I believe. So if you double the radius and you reduce the RPM by 12, does the force remain the same? No, the force is actually half. It goes down to 1.6. And the Morgel would have seen that if he had calculated this. So then if you look at the case of the Morgel's 100-mile radius theoretical gravitron, you can see the force is quite large at 3 RPM. It gives a g-force of 1,600. But if you look at the Earth with the radius of 6,371,000 meters and an RPM of 6.94 times 10 to the negative 4 revolutions per minute, which is what 1 day's rotation corresponds to, you see that the g-force is minuscule at 0.003. And then this spreadsheet, I won't talk about this one at length, but I just wanted to point out that you can hold whatever variable constant you want in order to, it depends on what you want to look at. In this case, rather than hold force constant, which is what I did for the main example in this presentation, instead of that I held the radius constant, and I held that at the radius of 1 Earth radius. So 6,371,000 meters. And I varied velocity and force. And you can see the results there. So, it depends. If, it all depends on what you're interested in seeing. You can choose to hold one variable constant or the other. Well, at any rate, that's the end of the show. And if you're a flat earther, I hope you learned something, or at least you enjoyed it. But probably not. Bye-bye.